Hello everyone, my name is Davi, and today I will be presenting StrObe, Streaming Object Detection from LiDAR Packets. 3D point clouds are an attractive sensor modality due to the geometrical richness they provide. In this visualization, we show detections from HDNet, a state-of-the-art full sweep detector. The ground truth is shown in gray. Videos like this are common in object detection and show how good our detectors are at finding the objects of interest in the raster. This visualization, however, hides a problem. A vehicle could move up to 5 meters in the time it takes to build a sweep. To illustrate this, in this plot we visualize the state of the labels at the timestamp of each individual LiDAR packet. We can see that the world is changing while the sweep is built. This is a problem for robotics, as our free space estimation will be off by dangerous margins. In this paper, we propose StrObe, a novel approach that minimizes latency by ingesting LiDAR packets and emitting a stream of detections. By leveraging a spatial memory and efficient operators, our model produces accurate detections while achieving latencies 6 times lower than fast full sweep detectors. This is the overview of our architecture. The network takes as input a LiDAR packet and an HD map, both of which are rasterized into BEV pseudo-images. We extract features from the LiDAR and map using our novel regional convolutions. This operator allows us to reduce latency by only doing computations where we actually have LiDAR data. Given a LiDAR raster, we first determine the minimal rectangle that encompasses all the points, crop this region from the original input, compute 2D convolution, ReLU activation, and group normalization, and scatter the result back into the original aspect ratio. Since individual packets only provide a fragmented observation of the scene, it is necessary to use history to perform good detection. We achieve this through a latent spatial representation of the scene that is maintained with a memory module. Our approach iteratively builds a global representation by remembering features from previous packets. Given a feature map from the current packet, we first retrieve the corresponding memory map, bilinearly resample the memory to compensate for ego motion, ensuring that both the current packet and the memory are in a consistent coordinate frame. We channel-wise concatenate them and use convolutions to learn the update function. The result is then stored back into the memory and passed to downstream blocks. Here, we show a visualization of the memory. We can see that there is high saliency around vehicles, indicating that the network is attending to important evidence. Lastly, multiscale features are bilinearly resized to a common resolution and channel-wise concatenated. The result then goes through one last block of convolutions, which regresses the confidence scores and box parameters. To train the model, we use sequential examples that contain 50 packets due to the temporal nature of the memory. We use the first 40 packets to warm up the memory and compute losses on the last 10. In particular, we use a multitask loss to optimize the model, as is typical in object detection. Having the losses, backpropagation through time is used to compute gradients across the memory. Note that no gradients are computed on the warm-up packets. To quantify the advantage of operating at the packet level, we introduced a latency-aware MAP metric. As opposed to the typical MAP, we use the green boxes instead of gray as the ground truth label. In doing so, the metric takes into account the data buffering time in order to estimate the quality of the detector. The results for HDNet show considerable degradation, particularly for vehicles, which are capable of meaningful displacement in the time it takes to accumulate a sweep. The other baselines show the same trend. This indicates that the performance of full sweep models in the real world would be considerably lower. Conversely, here we evaluate all models in a packet stream setting. We can see that our model far outperforms the baselines, which struggle with the partial observations from a single packet. While we didn't take into account model runtime for the metric, it is an important factor for safety since it indicates the minimum amount of time the system would require to be able to recognize an actor. We plot here the sweep build and model inference times. The fastest full sweep detector, HDNet, takes 128 milliseconds to complete, whereas our model completes in just 21 milliseconds, a 6-time speedup. In conclusion, we have introduced a novel detection method that operates from LiDAR packets. In doing so, we drastically reduce latencies and produce detections that accurately reflect the state of the world, as evidenced by our proposed latency-aware metric. Thank you.